Okay, now let's look at the natural or transient response of first-order RL circuits. And as we've already seen, there's the duality between capacitors and inductors as far as their equations. And we're going to see some very similar development between the first-order response of RC versus RL circuits. So, first of all, the thing to consider is that just as with RC circuits, a first-order RL circuit can have two possible forms. So we can always convert it into a Thevenin voltage and a Thevenin resistance connected across an inductor. Or we can convert our first-order RL circuit into a Norton current in parallel with a Norton resistance connected across that inductor. So just as with the RC circuit, we see that we can always reduce the remaining circuitry down to a Thevenin or Norton equivalent. So, have the same kind of situation with first-order RL as we did with first-order RC circuits. First of all, we're going to have a source that's going to create an initial condition in the inductor. And then the source is going to be removed by some kind of switching event. And then what we're going to do is we're going to look at what happens to all the currents and voltages in the circuit as the stored energy in the inductor is then dissipated and released into the circuit. So let's consider a possible circuit we can do that will fit into this. So let's create something like this. So let's look at a circuit, and once again we're going to have a switch. In this case, it's a switch that's going to open up at time t equals 0. And just as we did before, we're going to assume for t less than 0, we're going to assume that this circuit is operating in steady state conditions. So in steady state conditions, nothing's changing. Therefore, if we look at VL, the voltage across the inductor, IL, the current through the inductor, we know that VL is equal to L dIL dt But in steady state, di dt is equal to 0. Nothing's changing in the circuit, and therefore VL is equal to 0. Therefore, in steady state, the inductor acts like a short circuit, like a wire. So in steady state, our inductor acts like a short circuit. So let's go through and let's first consider what this looks like for t less than 0. For t less than 0, let's calculate IL. Well, for t less than 0, VL is equal to 0. So if the voltage across the inductor is 0, that means the voltage across this resistor is 0, and the voltage across this resistor is 0, because they're all in parallel. All the elements are connected in parallel. Well, if that's the case, I must have 0 amps flowing through that resistor, and 0 amps flowing through that resistor. So keeping in mind that this switch is closed, consider I0 is flowing into this node on the top. Where's the only place it can go? The only place it can go is through the inductor. So therefore, by KCL, IL is equal to I0 for t less than 0. Now, once again, we have to think about the property of inductors. In an inductor, the current cannot change instantaneously. So I sub L cannot change instantaneously in an inductor. Okay. Reason for that, of course, is since V is equal to L di dt, if di dt was equal to infinity, if I could get an instantaneous change, I would get infinite voltage, which of course we don't get. So I know that the current cannot change instantaneously in the inductor. And actually, I should spell this correctly. All right. So current can't change instantaneously in the inductor, and therefore, IL in the inductor just before the switching event at t equals 0 will be equal to IL just after the switching event, which is equal to IL at time 0, which of course is just our initial condition. Now hopefully this is all looking very familiar. We saw this kind of idea before with the voltage across a capacitor. Due to duality, we're looking at current in inductors versus voltage in capacitors, but the same kind of mathematical development. All right? So this is our initial condition. Now let's consider what happens when the switch opens at t equals 0. So at t equals 0, the switch opens. And now what do we have? All right. So for t greater than 0, the switch is open. And in this case, I've now got a single loop here. We note this current source and this resistor have no further effect on the inductor. We know that the current through this bottom wire must be equal to 0 because KCL tells us at that level current going in is equal to current going out, so current in one direction is equal to 0. It's got to be 0. So in this case, that means this is totally disconnected, and in fact, the only purpose of this RO resistor is just to give a place for that current to go. That's the only reason why it's there. So in this case, we're just going to let the current flow around here and just ignore this part over here. Here, I can go through and I can note that I have a single loop circuit, and that IL keeps flowing around that loop. In that case, I've got this voltage drop across the resistor, and I can write a KVL equation. And so by KVL, I've got that 0 is equal to, these are both drops, be equal to IL times R plus VL. And VL is equal to L DIL dt. And once again, we have a first order differential equation. And we note that the form of that equation is identical to the form of the RC equation we solved before. And therefore, we can solve. I'm not going to bother to go through the steps because the steps would look absolutely identical to what we did before for the RC circuit, except I'm exchanging L for C and flipping the V's and the I's. But if I solved, I would get the following. IL of t is equal to IL 0 times e to the minus R divided by L multiplied times t. And in this case, IL of t will be equal to I0, which is our value of the current. That's our initial condition, times e to the minus R divided by L times t. So that'll be our current for t greater than or equal to 0. So if we sketch this, we'll get something that looks like this. So if we sketch that current, it'll look like this. We'll have an initial condition I0. And then it will decay away. We have a switching event at time t equals 0. And once again, we have an exponential decay where IL of t goes to 0 as t goes to infinity. And in this case, we note that tau is equal to, in this case, L over R. And once again, it takes 5 tau time constants in order for this current to decay away. So IT decays to less than 1% of I0 by t equal 5 tau is equal to 5 times L over R. And once again, Henries divided by ohms has units of seconds. Doesn't seem intuitive, but that's how the units work out. looking at this, what is R? Again, R is equal to the equivalent resistance across the inductor or the Thevenin resistance across the inductor. So, once again, this is calculated after the switching event. So once again, we see the similarity between the RC and the RL type circuits. We have to calculate two quantities, the initial condition, and then we have to find the equivalent resistance across the inductor. And once we solve that, we have our answer, and we simply plug it into this form of the solution, which works for every possible first-order RL circuit. All right? Now, before I go and work a few more examples, I just want to spend a few moments kind of going over the methodology we have to keep in mind when we're working both RC and RL natural response problems. So let's talk about that in just a minute. So when we're analyzing a circuit and doing a first-order natural response, what do we have to keep in mind? First, keep in mind this. Only two quantities can be directly calculated using the first-order solution. First, we can calculate the voltage across a capacitor. So in an RC circuit, we're going to start with VC of t is equal to V naught e to the minus t over tau, where tau is equal to RC. The second quantity we can calculate is the current through the inductor in an RL circuit. So in this case, the form of the equation is IL of t is equal to I naught e to the minus t over tau, where in this case tau is equal to L divided by R. You always start here, always. It doesn't matter what the problem asks you for. You must start with the voltage across the capacitor or the current through the inductor, because those are the only two elements in the circuit where the initial condition, either VO or IO, persists across a switching event. So keep this in mind. This is, once again, an incredibly common error that students will make. they will try to apply the form of this solution to some other quantity in the circuit. And more often than not, they get it completely wrong. Okay? So you find these first, and then find any other voltage or current in the circuit using KVL, KCL, or the other equations you've learned. Find all other voltages or currents once you find VC of t or IL of t. So in this case, you'll use KVL, KCL. You'll use I is equal to C dV dt, or V is equal to L di dt. And so forth. So given this current and this voltage, once you have that expression, then you can find the rest by using the other equations you've learned. And we already saw that example with the RC circuits. And very shortly, we'll also look at that for the RL circuits. All right, so we've looked at this. Now let's go ahead and let's work a few examples of first-order RL circuits to once again show how similar this is to what we saw with the RC analysis.